I'm very delighted to welcome you all to this ninth seminar of this Indus seminar series. Today's speaker is Mr. Kalpesh Ghag, who is a PhD scholar at Department of Physics, University of Mumbai. He is working with Dr. Anil Raghav, who is an associate professor at Department of Physics, University of Mumbai, Kalina campus. Kalpesh obtained his master's degree in physics from the same department and pursuing now, a PhD over there. So his research interests mainly focus to understand the micro as well as macroscopic structures in interplanetary space and their effect on geospace dynamic as well as space weather phenomena. Particularly, he worked on for example, he worked on evolution of planar magnetic structure within the interplanetary coronal mass ejection and their role in geomagnetic storm phenomena. He also worked on thermodynamics of large-scale structures, cosmic ray modulation, MSD wave in its plasma, and so on. But his primary objective is to understand cause and effect of charged particle acceleration at the interplanetary shock through observational perspective. So today, he will talk about ICME-driven geoeffectiveness from planar magnetic structures perspective. He's also recently a nuclear fellow. So soon he will join the HOA for his one of the project. So with this, we welcome Kalpesh. So Kalpesh, now dice is yours. Please go ahead.
Yeah, I will share the screen first.
Yeah.
Yeah, is it visible?
Yeah, we can see.
Yeah, first of all, I would like to thank Indus to means this is quite a moment for me that Dr. Zubair is introducing me, because when I started my PhD there at Department of Physics and University of Mumbai, Dr. Zubair was our senior, and so he was first PhD student of my supervisor, and we just grown up while watching him, while seeing his research, and yeah, it's quite cherished moment for me that he is now introducing me on this platform. Thank you. So yeah, myself, Kalpesh.
My pleasure.
Yeah. Myself, Kalpesh, from Department of Physics, University of Mumbai. Sorry, I will just I apologize for the disturbances, because I am in your Trivandrum and there are lots of, I'm just near to the railway track and there are lots of trains are going there. So if you might cause any disturbances there, which apologize. Yeah. So, yeah, I'm talking about ICME-driven geo-effectiveness and insights from the planar magnetic structure. I will shift some focus to this because this is called as Magnemite, and this is a famous Japanese anime, part of Japanese anime known as Pokemon. So why I'm mentioning this here, these Magnemite are known to be a magnetic Pokemon. They are magnetic, and they give response to the electromagnetic radiation, electromagnetic signals. Once day in a particular episode, that episode name is "What's Your Name, Francois?" These all the Magnemites there, and that city behaves weird. Means they got some wrong signals. They emit some wrong electromagnetic signals. Yeah, and that's why the old people in that particular city were frightened. Later, they investigated that there might be some wrong signal from satellite, and that actually causing that all Magnemite to behave weird. A physics professor wearing apron shares this thought, and he tells that there is a solar storm at solar surface, and when it comes and hits our Earth, it disrupts our satellites, and that's why we observe such weird phenomena. So my intention to include this in topic is to say that it is a wonderful thing to all of our space weather and solar physicists, that how a particular thing and how academics things is used for the storytelling in a famous Japanese anime. So what they have told, is it true? Yeah, is it true? If you see, there are references. There is a famous book, that Space Weather, from his slogan, by these four authors, and there is introduction by Daniel Becker there, and he says that due to the charged particle, that electron, when they incident on any satellite instrument, whether they are high energy electron or whether they low energy electron, they are hazardous to the satellite. When they pass through this satellite, they might cause some different weird thing. They might disturb the satellite alignment and all. Other rather than the low energy electrons, might be responsible for the charging of that particular surface of the satellite. So all these things that they have shown are close to the reality. And is it up to the satellite? No. The space weather phenomena or the space weather effect has implication over the ground-based technologies also. We have lots of example, where the famous example is from March 1989, where Quebec or Canada suffers 9-hour blackout, and that blackout starts from 2 a.m. So that the another thing is GIC's event at New York in 1921. So there are lots of events are there where the ground-based technology as well as these satellites are affected by the space weather effects. So what are the space weather phenomena that are affecting? First is a geomagnetic storm, substorm, that I am going to cover in the further talk. Then ionospheric disturbances, auroras, ground level enhancement due to the charged particle which precipitates in our magnetosphere. Then the Furbush decrease, that is a cosmic ray modulation due to interplanetary structures. Then energization of particle in a radiation belt in a passage of ICME, CIR, or any magnetospheric disturbances. Then GICs. So all these are known to be a space weather phenomenon or the space weather phenomenon. So here we are going to discuss about the geomagnetic storm. This is a typical profile of geomagnetic storm here. And what's the mechanism for the geomagnetic storm? As we know, the southward component of magnetic field, when it reconnects with northward component of our Earth magnetic field, then it creates some passage to flow a plasma inside our magnetosphere, which enhances the ring current. This is one of the and the ring current which is revolving, the charged particle which are revolving in opposite way of the current that Earth mantle core has. So that's why the resultant magnetic field decreases, and this is the geomagnetic storm. And this is the simplest example, but in reality there are a lot of complexities are there. This particularly means, if we talk about the reconnection, we say BZ northward BZ from our northward component of magnetic field of Earth, as well as southward component of magnetic field of interplanetary space may reconnect. But this is not a simplest phenomenon. There are lots of factors are there. Some people say BY component is also there. Eastward electric field is also there. So for simplicity, we are assuming the southward component is coming. It reconnects and create a passage to ring current enhancement. And how it depicts? If you see here, there are typically there are many more indices are there which we can use as a proxy for the geomagnetic storm. But here we use generally CMATCH as well as DST. There is no difference between CMATCH and DST, but the CMATCH has a high resolution up to 1 minute or 5 minutes, where the DST is hourly data. So if we see here, the CMATCH value decreases, and again it recovers. 1 minute, I have to start my result here. Yeah. So this is known to be an initial phase of the geomagnetic storm, and this initial phase is due to the compression of the magnetosphere, or is due to the magnetopause enhancement in the magnetopause current. Then this is known to be a main phase of the geomagnetic storm, where the resultant magnetic horizontal component of magnetic field gets decreases, and this is a recovery phase where it again recovers. So this is a profile of a geomagnetic storm, an initial phase followed by sudden storm commencement, then main phase and then recovery phase. But sometimes this profile is not so simple. There are multiple steps in main phase as well as in recovery there. So this is simplest profile of geomagnetic storm, which is on 15 June 2000. And on the right side, it is a schematic representation of the physical process given by Dange et al. 1961. So before going to the geomagnetic storm there, I will introduce the magnetospheric current system there, especially two magnetospheric current system that we are going to focus. Generally, four magnetospheric current systems are there. Magnetopause current, that is we call it as Chapman-Ferrero current, then ring current, then cross-tail current as well as field align current. But specifically with particular this talk, we are dealing with magnetopause current as well as ring current. So the magnetopause current is a current that get developed in a magnetopause region where which is an eastward current. So when magnetopause current increases, it contributes to the addition of a total magnetic field. Whereas the ring current, there are two types of ring current as well, westward ring current as well as eastward ring current. But the westward ring current is more dominant one. Yeah, there is effect of eastward magnetic current is also there, but the westward that ring current is dominated one. So when that westward ring current increases, the total magnetic field went, so the resultant magnetic field goes down, and that's we called as a main phase of the geomagnetic storm. So this particularly ring current is due to the gradient drift of the charged particles. When they enter in magnetosphere, they experience the gradient drift there. So their motion is perpendicular to the direction of the magnetic field as well as the gradient of the magnetic field, and they start to revolve in the equatorial region. So let's introduce CMEs as well as ICME. We are here solar physicists as well as space weather physicists there. So we are aware of what are the CMEs and ICMEs. Typically, when we see through the remote sensing measurements from the SOHO, we see this. People see the three type structure, that is leading edge, then the cavity, then the core. But this picture, when the people see it through the in situ measurement, we see shock, then the turbulent region, and then the order magnetic structure called as a flux slope or a magnetic cloud. So the sheath is a turbulent region between the shock as well as and the boundary of magnetic cloud. So here it is a schematic diagram, but how we see in data, this is ACE data. ACE is located at L1. So if we see here, when ICME hits, we observe sudden increase in the magnetic field as well as the photon velocity, number density, and temperature also. We called this as a shock. Then after that, there is a fluctuation in magnetic field there. We call this region as a sheath. During sheath, we observed a high number density, high temperature. But when magnetic cloud comes, we see the clear rotation of the component of the magnetic field there. Then we observe low number density there inside the magnetic cloud, low temperature there, as beta is one of the factors that we use to identify the structure in situ measurement. Beta is the ratio of thermal pressure to the magnetic pressure, and when the magnetic cloud comes, it is a magnetic cloud carries the enhanced magnetic field, so the magnetic pressure increases, and due to which beta goes down less than 1. And so during magnetic cloud interval, we observe generally beta less than 1. So these are typical signature that we observed in the in situ measurement of ICMs. So these ICME no more swims alone in a solar wind. They constantly interact with other ICMEs. Solar wind is also there. They interact with the porotic interaction regions also. So during that, they may get deformed, they may get rotated, they may get kink, erode, lots of interactions are there, and that interaction depends on the type of interaction, whether there is ICME interaction, whether there ICME CR or ICME HSS interaction, whether that HSS is hitting from backside. If it is hitting from backside, then there might be a compression of the magnetic cloud. If ICME is in vicinity of HSS, then there might be an expansion of the magnetic cloud. When the two ICMEs interact, there might be a merger of the magnetic cloud. So there are lots of interdynamics is there, and it depends generally on the interaction, how that ICME interacts. So where people, Dr. Zubair and Dr. Raghav observed that during the ICME crossover during 21 November, they found that the cross section of the magnetic cloud got pancake. Means if you see here, this is a typical cross section of, we can represent this typical cross section of a magnetic cloud when it is non-interacted, but when it interact, this cross section becomes into some elliptical one. So during that, they also observed some signature, like this is a curve, and scattered points, a colored scattered point is data, and this fit or this rotation in theta and phi, that is azimuthal angle and elevation angle of the magnetic field, suggests some signature, and that signatures are of planar magnetic structure. So let's understand what's planar magnetic structure. So planar magnetic structure, PMS, are the structure where a magnetic field vector in interplanetary space are aligned in a particular plane. So if we consider the planes which are confined in the to elliptical plane, so this will look like this. And if they are looking, means if they are confined in the particular plane, then they will show this type of signature. They will show this type of, means their theta variation and their phi variation are constrained in this curve. So these are planar magnetic structure. Initially, Nakagawa, Palmario, and Raghav et al., as a Sheikh et al., observed this planar magnetic structure in the different domain of interplanetary space. They observe it in CIR, that is interaction between fast solar wind as well as slow solar wind. They observe it in sheath region also, ICME sheath region that I mentioned before, where the magnetic field lines are trapped around the shock region, and there we observe these planar magnetic structures. People observe, means Sheikh and Raghav et al. Observed this planar magnetic structure in a magnetic cloud also. So the occurrence of this PMS in a sheath region as well as in a magnetic cloud is a usual one. But in a case of magnetic cloud, there is quite debate, because people generally means when they do the MVA analysis or the minimum variance analysis of this flux flow, they generally observe the rotation of magnetic field, and they generally observe this signature. But this signature is not for all the magnetic cloud. There are some special magnetic cloud which are planar. Then generally people observe this signature. So this is typically as a magnetic cloud, as a PMS. When you observe another magnetic cloud, that might not a PMS. So that's not the case. You will observe this typical signature in every magnetic cloud. So the Sheikh and Raghav observed that out of 420 ICMEs, about 121 ICMEs, that is 29% of ICMEs are planar, where the remaining ICMEs, about 299 ICMEs, are non-planar. So magnetic clouds are not non-planar. So here is one case study there by Raghav et al. 2023, where this is a famous storm that happens on 21 November 2023. Sorry, 2003. So if we observe here, this particular CME was planar, and due to which they observe the extreme geomagnetic storm. If you see here, the CMAG index dropped down to minus 450 nanotesla, and you observe here the signatures of the planarity. The one of the components of the magnetic field shows a rotation there. The B1 star, B2 star, and B3 star are the components of the magnetic field after taking MVA. If you see here, these are typical parameter that shows the planarity to lambda 2 and with the lambda 3, where the lambda 1, lambda 2, and lambda 3 are the eigenvectors when we perform the MVA. Bn by B is known to be a planarity. Bn is a magnetic field component at a normal, and B is a total magnetic field. In ideal case, when we say that the planarity is maximum, this Bn should be 0 and this ratio should be close to 0. But some people refers that this ratio should be less than 0.20 there. So if this particular means this data shows or aligns with this fit, then we can say that yeah, this particular cloud or the particular structure is a planar magnetic structure. So this is another storm that recently observed storm on 23 April 2023. Here we also observed that the sheath is also planar, sheath is also transformed into quasi-planar structure, as well as the whole ICME is also transferred into the quasi-planar structure. And this is a famous storm that lots of publications are there. I mean, with this event that people observed the low latitude aurora during this event. So the one of the features that we observed here, we observed that during this 23 April storm, the magnetopause boundary shift towards 6 RE. So if you see here, this blue color data shows the magnetopause boundary measurement measured by Shu et al. 1998 model, and this red current measurement shows the total the BZ value measured by GOES, and this GOES is actually at was actually at 6 RE there at that particular time, and it shows some signature there. So it is the evidence of that magnetopause boundary is coming towards a 6 RE there. So this happens during 23 April geomagnetic storm. So with these all case studies and the statistical studies made by Sheikh et al. And Sheikh and Raghav, so what they found that during such planar sheath as well as planar cloud, the magnetic field component or the plasma parameter that are responsible for the geomagnetic storm are observed to be higher. Means if you see here, for non-planar ICME sheath, the average magnetic field was there about 9.17 Tesla, but in the case of planar sheath, that magnetic field enhanced to the 13.57 nanotesla. Same for the ICME magnetic cloud, which is as non-planar magnetic cloud, it is up to 8.66, but for planar magnetic cloud, it is up to 12.20. So if you see there is a lot of enhancement is there. Yeah. Then if you see BZ there, this is the main driving factor behind the geo-effectiveness of the storm. Then you might observe that for the non-planar case, the average BZ minimum was about minus 6.391. But in case of planar sheath, it is up to minus 15. So it actually enhanced by 2.5 times. But in case of cloud also, if you see it, initially the non-planar case, the average magnetic field, average BZ minimum was minus 9.46, but for the planar case, it is minus 30. You see, for the number density or for the proton velocity also, there are a lot of studies that say that number density and velocity are not direct contributor for the geomagnetic storm, but their combined effect with the dynamic pressure is also is one of the factor for geo-effectiveness. So people have observed that during the sheath, planar sheath and the planar cloud, the magnetic field as well as plasma parameters are enhanced. So whether these PMS are really geo-effective. We actually statistically investigated this phenomena. We divided this all type of CMEs into four categories. One, non-planar structure, another planar sheath, then planar cloud, then planar ICMEs. Those shows the PMS in sheath are called to be planar sheath. Those shows PMS in cloud are called to be a planar cloud. Those shows PMS as both in a sheath as well as cloud. We call it as a planar ICME. And we measure C match value, high C match value there, low C match value is also there during planar sheath, during planar cloud, as well as both planar ICME. So we have gathered a lot of data, and what we found this statistical distributions. It might observe confusing, but I will explain. If you see here, all the four rows, each row explain each type of categories of ICMEs. Means this first row shows ICMEs due to non-planar ICME, the geomagnetic storm due to non-planar ICME. Second one due to planar cloud, third one due to planar sheath, and fourth one due to planar ICME. And what we have found, the left side shows the distribution during of high C match value, left side shows distribution of a low C match value. So what we observe, the mean value for non-planar ICME C match high is 10, but if you see for the planar ICMEs, it is 31. If you see for the planar sheath, it is 15. It is greater than what we observe in a non-planar case. In a for low C match value, the mean value of that non-planar ICMEs that cause geomagnetic storm was about minus 57 nanotesla, but for planar ICMEs, it is about minus 98 nanotesla. For planar sheath, is it minus 58 nanotesla? For planar magnetic cloud, it is about minus 71 nanotesla. If you see here, this is a distribution, means if we divide these storms into different categories, that is weak, moderate, intense, and extreme. So weak storms are generally which show the C match, minimum C match value greater than minus 50 nanotesla. Moderate are between minus 50 to minus 100, intense between minus 100 to minus 200, and extreme, which shows C match low value less than minus 200 nanosecond. If you observe that in typical distribution of this extreme storm, the non-planar ICME shows generally 0.48% extreme geomagnetic storm. But in a case of planar, the percentage increases up to 9%. The intense storms are also there, and they are greater than non-planar, planar sheath, as well as planar magnetic cloud. So the planar ICMEs are observed to be more geo-effective, or this table shows the contribution of PMS in the different types of geomagnetic storm. So what are our major findings here? We statistically confirm our hypothesis that those ICME which transform into PMS are more geo-effective than those are non-planar ICMEs. Then the combined enhancement in magnetic field component as well as plasma parameter that found in PMS sheath as well as magnetic cloud is responsible for this geo-effectiveness. So this is due to the enhanced magnetopause current as well as ring current. So these are our major findings. So what's our next plan? We are so as we know, and as literature says, the most that extreme geomagnetic storms are there in the case of sheath, but we observe in a planar sheath also. So how this planarity enhances the geo-effectiveness of the sheath? That's our plan. Then all we are bothered about minus BZ and geomagnetic storm relation, but if that PMS carries plus BZ, and if such enhanced BZ is there, how it contributes to the magnetopause currents there. That's our future plan. Then how this PMS affects the ionosphere and magnetosphere coupling. Then we encourage those who modeling and those who are working in modeling and predictions. They uh, they 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 may consider this PMS correction in their particular modeling, so that we can generally predict these storms, these extremes and intense storms there. So how this PMS is responsible for charge particle acceleration and dynamics in a outer magnetosphere, particularly in the radiation belt. So that's our future plan. So these are the publications related to these topics. This type of works that we generally do in our Department of Physics. Generally, we work in large scale structures such as ICMEs and as well as CIRs. We see how these CIR and ICMEs are there for cosmic ray modulation. How's the CMEs and CIRs thermodynamic evolution. Then some small scale structures inside the cloud sheath as well, and how they're responsible for the particle energization. That's our interest. And yeah, thank you.
Thank you so much, Kalpesh, for a wonderful talk. So the dash is open for the questions. You can raise your hand if you have any questions. We have one question in the chat box. Yeah, we have one question in the chat box. Debesh, you want to ask, or shall I read it for you?
Yeah. Hello. I can ask. Yeah.
Yeah.
Thanks. So, yeah. So it's a very nice work. It's really interesting work. Yeah. So I just want to ask you. You said that inside the cloud you have seen the planar structures. So I just want to ask you where exactly you see those structures. So is it in the front part of the cloud, or in the back, or in the middle? Something like that.
Yeah, there is distributions there. Means if you refer the Sheikh and Raghav et al. 2022, I think at 2020, then 2022 there, then then there is a statistic there, how much percentage of the PMS they are from at leading edge of the cloud, and how are they at trailing edge of cloud or the middle. I actually don't know how the percentage there, but I know that the percentage is mentioned there. I will encourage Dr. Zubair. Can you?
Yeah, Debesh, generally, that paper what Kalpesh was talking about, that deals with the scenario where you observe whole ICME sheath or whole ICME cloud transform into this called two-dimensional structure, which we say planar magnetic structure. But I also know that there are cases where you observe only part of the sheath or part of the ICME metric cloud, either rear part or the front part, transform into PMS, not the whole structure. So there are cases where you observe only certain region of, like front 1 hour, 2 hour duration of this cloud, rear part of the cloud can also transform into such kind of structure. Basically, it is like, compression from either from the front side or from the back side. So your structure is not like a 3D spherical geometry cross section, but is somehow, flat and compressed kind of structure you can observe. Yeah, there are cases.
Okay, so yeah, it is actually based on the interaction between the
Yeah,
ICME
it is
and the
interaction between
Yes,
ICME and
yeah.
wind, or whether ICME and ICME interaction, type of interaction.
Yeah.
Okay.
Basically it deals with this kind of interaction.
Yeah, so I have another question. So you just mentioned, or you actually showed that for the planet structures, the B is larger. Magnetic field strength is larger. So what's the reason for that? Like why it is so?
This is might due to the compression of the magnetic cloud. So that so if there is an interaction, So it restricts a particular this field into particular plane, and that's why we observe this enhancement in the B or particular magnetic field vector. It is due to the compression.
So yeah, okay, yeah, because of the compressions actually, the field lines are close to each other.
Yeah.
Okay, thanks, yeah.
Yeah, so Anjali, you can mute yourself and ask the question.
Yeah. Hi, Kalpesh. Nice talk.
Yeah.
I want to ask that, like in the magnetic cloud, can you just go in the magnetic cloud plot, that in situ plot, in any one plot?
Yeah.
So, you are saying these clouds are planar magnetic structures. So, can this be multiple? A ICME can contain multiple flux ropes. Like you can see the rotation of theta is 2 times from south to north. Like in other cases, 2 times the rotation of theta.
Yeah. It is depend on whether sometimes what happens is there is a continuous eruption or the consecutive eruptions of the flux rope there, and when they travel somewhere, some reading part may get overcome, and there might be a merger of these clouds, and due to which we may observe two clouds or the two particular flux rope there in a cases. So if you see here, there might be a different graph here, so it is quite helpful to understand. Yeah, if you see here, you see two means here it is first flux rope there, and the trailing part is a second flux rope there. It's a small flux rope there, so this is two consecutive flux ropes are there, which are, yeah, you're right. Means what you're asking, we might observe a two flux rope also there in the case of magnetic cloud engines.
So they are basically interacting.
Yeah. There might be interaction. Yeah.
Okay. Thank you.
Hello. Hello.
Hello.
Yeah, we can hear you. Hello.
Yes, I have a basic question. I am now MSc pass out student, so that's why. What is the connection between CME and geomagnetic storm?
Yeah. I
Is
will
it?
explain here.
Yes.
Generally, what happens for the geomagnetic storm, as I explained here, if any southward component of the magnetic field is there, when it reconnects, it causes some passage that this particular plasma comes inside our magnetosphere. So we need southward magnetic field, and who carries that southward magnetic field? ICMEs. ICME carries that southward magnetic field. So it depends on how the magnetic topology of the 1 minute, I will explain with another plot here. So you might observe here, this is a last panel of the plot, which shows the C-match indices there. This is initial some shock sheath region, and this is magnetic cloud region. If you see here, when a BZ component, which is shown by, we will expand this thing. If you see here, when this magnetic field BZ components turn southward, you observe a decrease in a C-match index. So this shows that the C match index is getting decreased. So what is C match index? It is horizontal magnetic field component. Your horizontal magnetic component is going to decrease. So on the basic form, so how we can decrease a magnetic field? Either we can control their source, otherwise another magnetic field of a different orientation should be there. Yeah, but we cannot do that, control the source, because the geomagnetic field is due to Earth rotation. So there might be a different orientation magnetic field should be there. So how that different magnetic field comes in picture? There might be some different current system there, and that current system is a ring current system. The ring current is there at about 6 RE there. So there it is revolving. Some charged particles are there that are revolving in an opposite way, where in the westward direction. So if that current increases, then oppositely oriented magnetic field increases, then the resultant magnetic field will decrease. So how the ring current increases? The ring current population increases to the solar transient. So how the solar transient come into picture? Here, with the reconnection of southward magnetic field with the northward magnetic field of the Earth. When that reconnects, then there is a plasma passage for the plasma. It contributes to the ring current, and due to ring current enhancement, we observe a decrease in a magnetic field there. And this is known to be a main phase of the storm. But when this ICME pass, or when this BZ turns southward, you may observe there no reconnection, then there is no plasma flow in magnetosphere, then the recurrent again recombines, because these are the charged particles, ions and electrons, they recombines there, then the ring current goes down, and during that time we observe a recovery phase here. Then again the magnetic field recovers. So that's the relation between the ICME and geomagnetic storm.
Okay, thank you very much.
Yeah, Kalpesh, we have one question by Ritika Tiwari. She's a master student and interested in CME. So her question is like, I read somewhere that cavity is highly magnetic region. Can you please tell me what should be the reason?
What
At
do
a
you
cavity.
mean by cavity? Sorry.
Yeah. So
Highly
the
magnetic.
question is like, cavity is highly magnetic region. She's talking magnetic cavity, which is associated with the CME. Okay? So they are highly
CMEs,
magnetic
yeah.
region. So yeah,
I
why it is so? Why it is
Yeah.
highly magnetic region?
this is due to the flux rope. It carries the flux. So I actually don't have that understanding at the phenomena from the core cavity and that region. So I not understand that question completely. Sorry, but this is due to there is a presence of flux rope there, and that's why this region is really magnetic. Sorry, am I right or wrong? I don't know, but I didn't understand this question. So,
Ritika, if you want, you can ask the question directly to the Kalpesh.
yeah, you can elaborate more.
Yeah. So I have one question for you.
Yeah.
The first question is, does BY interplanetary magnetic field, BY component, plays an important role in magnetopause current?
There is one study that I read that BY is causing the asymmetry in the charge particle in a magnetopause region. There is one paper that I think what I read. So there might be a effect there, but again the magnetopause current is more generally related to the dynamic pressure, which consists of number density and velocity. So I have doubt, but yeah, it's interesting to see how this BY is contributing to the magnetic.
Thank you. We have one question in a chat by Ashwin. The question is, can we able to differentiate the filament originate CME and the sunspot originated CME using in situ measurement with Omni data?
sorry, I don't have that much understanding in this.
Maybe you can write to him.
Yeah.
Yeah, email. Maybe he can respond. Okay. So, or if someone can answer this question, then you're most welcome.
Yeah.
Yeah. So, and another, there is one question. Yeah, Mahendra, you can ask the question.
Hi, Zubair and Kalpesh.
Yeah.
Good. Kalpesh, nice talk. So I have one question. Recently enter into your field actually. I want to ask a few questions. So during the ICME, so what are the profiles of temperature of proton and the velocity of proton and number density of proton and magnetic fields? So the magnetic field is suddenly enhancement is there, right?
Yeah, during shock. When shock is there, sudden enhancement.
In the same slide, so there is a sudden enhancement is there. So basically, how can we find the ICME actually?
Generally, if you see here,
Hmm.
1 minute, huh?
Yeah.
1 minute. Yeah. If you see here, means if you see the ambient solar wind conditions, I can explain with a different plot as well. This is my clear. The shock we observe is quite clear. So if you see here, this region means if you see the shock, there is sudden enhancement. Okay, fine. Then after the shock, you might see some fluctuation in the magnetic field, total magnetic field, as well as in a component of the magnetic field. So this region is a sheath region. So this is shock. The shock is identified with sudden increase in the magnetic field, sudden increase in the proton velocity, sudden increase in the number density also. So these are typical 3 criteria for shock. There is another theoretical criteria called ranking Hangnot condition. So there is a catalog by Kilpua et al. Which identifies different type of shock there, and you might see this typical ICME shock listed in that catalog as well. So there is enhancement, sudden enhancement in B, VP, and NP is characteristics they are the characteristics of the shock. If you see a magnetic cloud there, the profile of the magnetic field is different. You might see the sudden decrease as a constant decrease in a magnetic field, a rotation of magnetic field component there. Generally, BX. Sorry, this BX, BY, BZ. The blue is BX. So you might see there is not much variation in BX, but you observe BY and BZ variation much. Then the beta is actually less than 1 in the case of magnetic cloud, because its thermal pressure upon magnetic pressure ratio is there, so magnetic pressure increases, that's why it goes down. The number density is also getting down, and the temperature is also down during the magnetic cloud, where in the case of sheath, where the region between shock and the boundary of the cloud, the number density temperature is observed to be increased. This is typical signature and the profile of shock, sheath, and cloud in the in situ measurement.
Okay, thank you.
Yeah.
Yeah, we have another question in the chat from Anjali Agarwal. The question is like, as in situ measurement using Omni provide only plasma magnetic field measurement of 1 AU. So probably it will be able to differentiate. Okay. Okay, I think that is from the previous discussion. Okay. So if we have any question, then please go ahead and ask the questions or put it in the chat box. We will read it for you.
So one more question, Kalpesh, can I ask?
Yeah, go ahead.
During this ICME, so what are the dynamic changes of the solar wind velocity?
Generally, in the solar wind profile is interesting there. The solar wind profile actually depends on how the ICME is expanding. Means if you see here, the typical profile is during the during shock, the velocity, solar wind velocity increases. In the case of magnetic cloud, it constantly decreases. So there are a decreasing profile is there in a velocity. But if you observe, in some cases, you may observe there is an increase in velocity during trailing edge, and after some time, then you might observe that there is an interaction of magnetic cloud there with preceding solar wind. So at that time, you might observe the increasing velocity, but generally in a case of magnetic cloud, the profile of velocity is observed to be decreased.
Okay, thank you.
Yeah, normally this decrease in velocity profile during a cloud, it suggests that your cloud is expanding in an interplanetary space.
Okay, thank you.
And this constant speed, during the sheath region suggests that your region is compressed, see the fluctuations, a lot of fluctuation in the sheath region, the velocity component. So it is more or less moving with constant speed, but a bit fluctuation in it. But your cloud is a closed structure, so it is expanding. So that's how your velocity, using in situ observation, you can see that velocity is decreasing.
Decreasing. Okay. Thank you, Jubair.
You're most welcome. So we have one more question. If BZ is northward, but your dynamic pressure is very high, so in that case, can we expect geomagnetic storm or substorm to happen?
Yeah, in case of busy when it's northward and of dynamic pressure high, in such case we might observe the strong compression there, and I think that might leads to not directly with geomagnetic storm, but it might observe a different magnetospheric phenomena should be there at that time. I'm not clear about direct geomagnetic storm, but due to such high compression, we might observe the tail side things were there. Due to high compression, that magnetopause boundary shift, we might observe some dynamics in the radiation belt as well as. But I doubt whether it directly links to the geomagnetic storm, because for the storm we need the ring current enhancement there, and if the BZ is positive, but if the dynamic pressure is increased, we might observe compression, not directly geomagnetic storm. That my intuition.
Yeah, thank you. So if we do not have any question, then let us thank Kalpesh for this wonderful talk. Thank you, Kalpesh.
Thank you.
Yeah.